In this video, we will discuss modeling with attributes. We will discuss different perspectives on how semantic information is used in spatial modeling and in coding. In the process, we will define what we mean by modeling with attributes. Semantics is the linguistic and philosophical study of meaning in language. Such languages include programming languages and formal logics. Consider the semantics of this image. When we look at this image, we see a bunch of colored stripes. But there is a meaning behind those stripes. The image is a data visualization developed by Professor Ed Hawkins. It used colored stripes to visually portray long-term temperature trends. Each line represents the average annual global temperature, from 1850 on the left to 2019 on the right. The image is a nice example of semantics. For the stripes, the semantic information is not explicitly represented. It is implicit in the color values. Spatial data can also have semantic meaning. And just like the stripes, the semantics of spatial data is often also implicit. Geometric entities such as points, polylines, and polygons have no semantics on their own. We may look at a model and perceive certain semantics. However, if the semantics is not explicitly represented, then it is not computable. For computational thinking, computability is key. Let's have a look at 3 approaches that modeling systems take when it comes to semantics. We refer to them as no-semantics, hard-coded semantics, and user-defined semantics. The no-semantics approach is typical of many CAD systems. Such systems uses data representations that typically have very limited support for semantics. When one looks at many CAD software applications, the only way of adding semantics is through grouping and layering. Geometric entities can be placed in certain groups or layers. And these groups or layers can then be given names with semantic meaning. In the example, a dialog box is shown, where some layers have been defined. The entity being modeled may be a building. Each floor of the building has a layer, with sub-layers for walls and doors. This is a useful way of adding semantics. But let's say you wanted to add information about the total area to the floor. This would not be possible. The second approach is hard-coded semantics. This approach is exemplified by BIM software. The approach is based on a data representation called a product model. A product model is a representation developed specifically for a particular type of product. In this case, the product is a building. Such product models tend to be highly detailed and specialized. When we look at the menu of tools, we can see that there are tools for many standard building elements. For example, walls, doors, windows, and so forth. When you use these tools, your model will automatically contain detailed semantic information. But hard-coded semantics tends to be most effective when the design is quite standard. In the example, we can see that the building being modeled is not very standard. As a result, it is not clear what tools would have been used. There is nothing that looks like a wall, door, window, column, beam, slab, and so forth. When coding, we tend to use product models to export the final result. But in the process of generating the model, we may need a more flexible solution. The third approach is user-defined semantics. This approach is exemplified by GIS software. The data representation in GIS system is much more flexible. Typically, they support 2 types of data, called raster data and vector data. The vector data usually consist of points, polylines, and polygons. The key that makes GIS software so powerful is that users can overlay their own semantics on top of both raster and vector data. This semantic overlay is made possible through the use of attributes. For example, for the vector data, attributes can be defined on any set of points, polylines, and polygons. For coding, such an approach is very useful as it allows us to attach data directly to geometric entities. We can apply semantic constructs in our code in many different ways. When it comes to spatial data, representations that integrate custom semantics can be powerful. The coding example shows two approaches. We assume that we have 3 panels, one facing north and 2 facing up to the sky. In the first approach, the data representation used is a pair of lists. 2 separate lists are used, one for storing some semantic data, and another for storing the panel entities. But managing these separate lists becomes error-prone. In the second approach, the semantic data is attached to the panel entities as an attribute data. There is then just one list, integrating both geometric and semantic data. This opens up many other possibilities, such as semantic querying. Attributes are data that can be attached to the geometric entities. In this example, we can see an attribute table, where each row represents one polygon. The polygons have a set of user-defined attributes. Each polygon has a name, a material, an area, a perimeter, and a label indicating which direction it is facing. The data representation allows all this data to be directly attached to the polygon entity itself. Mobius supports user-defined semantics similar to the GIS approach. However, the approach used in Mobius is more flexible and general. The diagram shows the sub-entities for a polygon. In this example, the polygon has 1 wire, 4 edges, 4 vertices, and 4 positions. Attributes can be added to any of these entities. In the Möbius model, geometric entities are organized into a hierarchical data structure. There are 3 main layers. At the top are collections of objects. In the middle are objects. And at the bottom are positions. The objects in the middle layer include points, polylines, and polygons. Each of these objects also has topological sub-entities inside them. Attributes can be added to any entities and sub-entities.